Let me start with something that's not so recent. I want to start with the Cauchy-Kubota formulas. So what do? We start with a convex body in Rn, and this curly K is my notation for the space of convex bodies, compact convex sets in n-dimensional space. And I take a hyperplane randomly. So I choose my Grassmannian, and it doesn't have to be a hyperplane, actually it can be a j-dimensional subspace. And I choose it randomly according to a half probability measure on this Grassmannian, and I want to calculate the volume of the orthogonal projection of this guy. So this is the formula I've written here. Let's see whether this works. Yes. And this is, of course, the expected value of a j-dimensional volume of a random projection of K. This is a well-known classical object. This is just the J's intrinsic volume. So I put here some normalizing factors which appear. So this kappa j is just the j-dimensional volume of unit body Rn, but these normalizing factors won't be too important for us. This is my way to define the J's intrinsic volume. And of course, this is a well-known notion from the geometry of convex bodies, and let me just put a couple of equivalent definitions on the next slide. For example, you can use differential geometric definitions. So if we have a convex body with smooth boundary, then, for example, this here would be the n minus j minus 1th elementary symmetric function of the principal curvatures of this boundary. And you integrate over it, and you get some normalizing factor, and you integrate the boundary with respect to the Hausdorff measure of the boundary. Or you could do this as a similar thing if you look at radii of curvature of a convex body. Or you use the most classical way to do it. You use the Steiner formula. You calculate the volume of a parallel body of K and see that this is a polynomial in this factor T, and the coefficients are the intrinsic volumes, and there are other ways to define intrinsic volumes. And what I want to talk about is analog notions in the theory of convex functions. So this is again my formula, and actually let me extend it a little bit. So if in the previous version I had the volume of the projection. If the body is j-dimensional, then the volume is the same as the intrinsic volume, so I can write the formula out in this way. And then I could also, and this is what Kubota was doing, extend this for any k greater or equal to j. This is an extension of the same formula. And what I want to talk about is, can we do something similar if I talk about functions? So I have now a function, u, that is convex. It has some other properties, lower semi-continuous, proper. We'll come to this a little bit later. How does such a formula look like, a Cauchy-Kubota formula look like for convex functions? So of course, one way is to translate each notion to the new setting. And what's kind of maybe easy to do, or there are approaches to this, is to define the projection function. So if I look at, again, a k-dimensional subspace, E, and I can define the projection function in this way. And the easiest way to imagine what's happening is you identify the convex function with this epigraph, project the epigraph to this space, and look at the function that describes this epigraph. This is what's kind of can be seen in this picture. This picture is stolen from one of my co-authors, Fabian Musnik. And I think this is an easy way to remember this formula, which means here we at least have this projection well defined. We still have the same Grassmannian, the same measure. This is not a problem. So what we still need to define is a volume of notion of intrinsic volume for convex functions. Of course, the AP graph is not bounded, so maybe it's not a good way to just plug this in. And of course, there are many ways to approach such a problem. And on the previous slide, I had a couple of equivalent definitions of intrinsic volume. I could take any of this and try to generalize this to the functional setting. What I want to do is something a little bit different. I want to use an axiomatic approach to the theory of valuations on convex bodies. So this is my definition, and it's of course not my definition. It's the definition that we use. A valuation on convex bodies is a function, and here I'm looking now at real valued valuation, that fulfills this basic property, this inclusion-exclusion property. So if I take two convex bodies, such that the union is again a convex body, I require that set of K1 plus set of K2 is equal to set of K union K2 plus set of K1 intersected with K2. So this is always a convex body, so I don't have to require this. And this is, of course, just a property, finite additivity of measures, a very basic property that a function can have. And in particular, volume has this property. So if you think about orthogonal projection, they don't destroy this property. So intrinsic volumes have, through this projection formula, this property. And similarly, you see that if I look at the functional I have defined a little bit more generally, if I take the Grassmannian of k-dimensional subspaces, also this functional defines a valuation because the integration over the Grassmannian doesn't destroy the property. And this function has nice additional properties, in particular geometric properties. It's translation and rotation invariant. Of course, if you translate a body, doesn't change the volume of the projection. And the reason that it's rotation invariant is, of course, you take the Haar measure on the Grassmannian. So this gives you the rotation invariance. And you can also get that the function is continuous. This is maybe a little bit more involved, but not difficult to see. And it's also easy to see that it's J homogeneous. If you scale by a factor, you get, that you scale by a factor t, you get t to the j times the functional. And there's a celebrated result by Hartwig from the 1950s that says that a function on the space of convex body that's continuous, translation and rotation invariant, and evaluation, that is the case if and only if it's a linear combination of these intrinsic volumes. So this space is n+1 dimensional, so you just have to find this n+1 constants. And moreover, the trivial consequence of this, if you know that the function is in addition J homogeneous, it's just a multiple of the J's intrinsic volume. Which means for our question, that our functional is a multiple of the J's intrinsic volume. So the only thing that we have to determine is to determine this one constant. And you can determine it by plugging in, let's say, the ball. So that's an easy task now. Okay, so what does it mean for my question? I wanted to have a notion of intrinsic volumes on convex functions. I use the same approach. So let's first talk about valuations. You can more generally define valuations on function spaces. So I take on any set, I take a space of real valued functions, and I replace my union and intersection by the pointwise maximum and the pointwise minimum of the two functions. This coincides with the definition I had before. If you think of functions described by the AP graphs, for example. And I define a valuation as a functional with the property that we have set of f plus set of g is equal set of f max g plus the minimum of f and g for all functions where everything is defined. And if I want to use this approach, I need classification results. So the question is classification of valuations on the space of convex bodies, convex functions, or more generally on classical function spaces. And this is a question I have been interested in for the last couple of years. And here are some results. And I think this is the first paper, even so you don't see this by the year. So I started to look at this at valuations on Sobolev spaces and with some of my students on LP spaces, and Andrea started to look at this maybe independently for spaces of convex functions, and later we joined forces, and the next couple of results I want to describe our joint work with Andrea Colasanti and Fabian Musnik. But there are also results of valuations on, for example, continuous and Lipschitz functions. This is a group in Spain, Villanueva and Tradatheta, and also many people that are somehow connected to Vienna. Okay, convex functions is well known. Just to introduce my notation, I take convex functions, I allow them to attain the value plus infinity. This is something that's kind of classical in convex analysis. I want them to be lower, semi-continuous, and proper. Proper just means that they're not identically plus infinity, which would make some trouble. And in particular, if I take a convex body K, and I define this convex indicator function, the function that is 0 on the convex body and plus infinity outside, this belongs in the space. This means I can embed the convex bodies in the space of these convex functions. And there's a kind of well-known topology on this space that we will use. This is called epiconvergence, or it's also called gamma convergence in the calculus of variations. And this is a formal definition here. Basically, as long as everything is finite valued, this is just pointwise convergence or local uniform convergence. And at the places where you're on the boundary, you have to be a bit more careful. And since we aim for something like a Hartwiger theorem, we need some geometric notions. But before that, actually, I want to look at a subspace. This is called so-called supercursive functions. Supercursive just means that they grow more quickly than the linear functions. So this is a proper subspace of the space that we're considering, and this is known under all kind of names. And I will give one explanation why this is a natural space to consider a little bit later. And this is my notation. This SC stands for supercursive. So now to the geometric notions, I hope. Yeah. So we look at so-called epi-translation invariant valuations. So translation invariant would just be a look at translation in the domain, but now I want to also be allowed to translate the whole epigraph. So this means I allowed here a translation in the domain, and I'm also allowing addition of a constant. So if I take the epigraph of a function and translate it, then I want that my functional doesn't change. This is a strong assumption, but it makes it possible to build a theory that is similar to what we have for convex bodies. And similarly, we define an epi multiplication. This is this little square here. I don't know if you can see this, but anyway, this just corresponds to scaling the epigraph of the function. So you just look at again at the operation in Rn plus 1 if you want so. And then again we have epi-homogeneous of degree I if we have this scaling property similar to what we had for convex bodies. And a while ago, together with Andrea Colasanti and Fabian Musnik, we showed that if you have a functional on this space that is continuous and epi-translation invariant valuation, then this implies that it can be written as a linear combination, as a sum of homogeneous components. So this is something like a homogeneous composition. So this means if you want to give a classification, you only have to look at I-homogeneous parts. And this corresponds to a result on convex body that was first stated and proved in a special case by Hartwiger and by McMullen, Meyer, Spiegel, 1977, there are proofs of this in full generality. And our result is based on this result by these authors. But this also means that it's kind of possible to look at all these components separately, and in particular, the first component, the epihomogeneous component, behaves nicely. So we have the following result. If we have a valuation that is continuous, epi-translation invariant, that is epihomogeneous of degree n, so the highest degree that appears in this decomposition, then this is the case. And this again, now again, is a characterization theorem, and if and only if statement, if there exists a continuous function with compact support, zeta, such that set of u is equal to the integral over the domain of u, zeta of gradient of u of x dx, for every function in my space. And domain here is the set of points where my function is finite. Otherwise, it doesn't make to define the gradient. Gradient, of course, of a convex function is defined almost everywhere, so everything makes sense. And this corresponds to a result by Hartwiger. It's a little bit later than the one I had on the slides before. That if you have a continuous translation invariant valuation that is homogeneous of degree n on the space of convex bodies, then this is just a multiple of volume. So in a certain sense, we have something that corresponds to volume in our setting. Correspondence is not perfect, but it plays the role of volume in a certain sense. And then, since we wanted a version of the previous Hartwiger theorem, we have to define something like intrinsic volumes. And what we have is following definition. We look at a particular class of functions. So on the previous slide, we had a function on Rn that had compact domain. Now we look at a function on the open interval from 0 to infinity that has bounded domain. This B does just stand for bounded domain. And that has a particular behavior at 0. So at 0, this goes to infinity, or is allowed to go to infinity. And for these functions, we define this integral in the smooth case. So this is just twice differentiable, this positive curvature. And this here is just the, maybe down here, this is just the k elementary symmetric function of the eigenvalues of the Hessian of U. So this is similar to what we had in the differential geometric definition of intrinsic volumes. We had the elementary symmetric function of curvatures, and now here we have elementary symmetric function of eigenvalues of the Hessian. And these are objects that have been studied a lot. In particular, if you put this together with the Lebesgue measure, this defines in the smooth case the so-called Hessian measures, which were studied in the for partial differential equations and also in the measure theoretic setting by differential for the PDT case. Tudin and Wang have contributions here, and in the measure theoretic setting, Colasanti and Hook, a couple of papers. And what we showed is that you can extend this definition to a valuation that's defined on all convex functions, super-recursive convex function. And this extension is still continuous epi-translation and rotation invariant. So this is what we want to call functional and intrinsic volumes. And the reason for this name is the following theorem. Well, actually, let me, before I give the theorem, just one remark. If I plug in this indicator function, the convex indicator function, then this gives back the intrinsic volumes. So in this sense, this is really compatible with our embedding. And we have the following result. If you have a continuous epi-translation and rotation and valuation, then this is a linear combination, then this is a sum of such intrinsic volumes with given functions from this particular class of functions. And this is an if and only if statement. So this means this looks in a certain way similar to the result by Hartwiger, and this is also why we call this function intrinsic volume. Of course, here we really have a linear combination, and here we have this kind of added complication that we have much more freedom in the choice or in the last axis.
In the previous slide, you had a formula. Is it? It's for C2 plus.
Yeah.
The way you extend it, is it using like Alexandrov Hessian, or do you does the formula make sense?
So the formula makes sense for a large class of functions using just the Hessian measures, but not for all of them. So more or less, you still have a singular integral. So you have to take something like what is called principal value of this. So this is not what we precisely showed, but basically it can be extended on a large class of functions. You extend it to Hessian measures, but not in general.
I also have a question about the uniqueness statement here.
The uniqueness is just...
What does it mean?
If this holds on the smooth bodies, then there's just a way to extend it.
But you fix the theta then?
Yeah,
okay.
This fixes the theta. Okay. So this is the Hartwiger theorem, now the functional version. And now let me return to the question I started with. And we can now do Cauchy-Kubota formulas. So this is just, everything is just replaced by the equivalent notion. And we have this these formulas. And this holds for all convex functions. Here, it's a little bit different from before. We have here a function theta. The theta is determined by, well, here we have a theta in our class, and this determines a function xi in the corresponding class that are connected through this formula. And this connection is this kind of integral transform down here, and this is an invertible transform. So you can go in both directions. So this is the Cauchy-Kubota formula, and basically I've shown you the proof. The proof that I gave for convex bodies also works here, up to the added complication that you have to be a bit more careful with this. Before I was saying there's one constant, you fix it by one convex body, and here you have a function, you fix it by a family of convex functions. And there's also proof using Cauchy-Kubota formulas for curvature measures. And there are also now more recently extensions by Daniel Hug, Fabian Musnik, and Jacopo Olivelli for more general Cauchy-Kubota formulas for more general functionals. Okay. And another remark, you can use this if you just put j is equal to k and use the characterization we had before for valuations that are n-homogeneous of degree n to get an explicit formula for this functional intrinsic volumes that works for all functions at the same time, and you don't have to distinguish between smooth and non-smooth functions. And this is just both resides plugged in. You get such a formula where you have to integrate over the domain of the projection of U and over the Grassmannian to get a formula for the functional intrinsic volumes. And let me also add that you can translate all this to different settings. I mean, you could translate this to log concave functions if you want. I don't want to do this now, but it's no problem. This is possible. But you can also use duality to translate it to a different class of convex bodies. And this is the next slide, I hope, yes. So if you use the Legendre transform, then it's a well-known result that if I denote by this the space of finite valued convex functions, so now I don't allow the value plus infinity anymore, then this Legendre transform of this space is the space of supercursive function, and this is a continuous bijection. So you really can jump from one to the other. This is the same. Everything can be translated. In particular, everything we did do with valuations can be translated. You can define something like a conjugate, convex conjugate valuation by defining just Z star is now defined on the finite valued convex functions by defining Z star of V is equal to Z of V star, where V star is a convex conjugate of V. And everything goes nicely. You can translate what translation invariant means, and we call it dually translation invariant just because it's a dual notion. This corresponds now to adding a linear function, and this doesn't change our function. These are just well-known properties of the Legendre transform. And you can also talk about dual epi-translation invariant. This means if you add a linear function and a constant, it doesn't change your function. And now the result reads as follows. Set on the space of finite valued convex functions a continuous dually epi-translation invariant rotation invariant valuation if and only if it is a linear combination of these functionals. And I have omitted the upper n here just to make it not too crowded. And you can easily get what these functionals are in the smooth setting. These are such integrals. So now you have an integral over Rn again in the smooth setting, theta of norm of x. Again, the J's elementary symmetric function of the eigenvalues of the Hessian appears here. And this can be rewritten also using a different approach. You can write this as through such integrals. So this is a different way to write the function intrinsic volumes. So before we had the Hessian measures, we had this J's elementary symmetric function of this eigenvalues of the Hessian. This corresponds to a mixed Monge pair measure. And if you use a different mixed Monge pair measure, you take the mixed Monge pair measure where you plug in the function Vj times and the support function of the unit ball n minus j times, then you get an easier or simpler representation of these function intrinsic volumes. So I just wanted to show this formula because this is a kind of motivation for the next type of questions. We had this function intrinsic volume that involved these Hessian measures, and now we have this dual version that involves this Monge pair measures. And the question is it clear what kind of measures should appear in such questions? And of course, if you like valuations, then you ask how can you classify valuations in such a way. And this is what I want to talk about for the rest of my time. And this is more recent work with Jin Li, who was a postdoc in Vienna and now is back in Shanghai. And as before, I want to start with the setting of convex bodies. So what can we say about measure value valuations on convex bodies? So I want to associate with the convex body a measure. So these are now the set of radon measures on the sphere with a weak star topology. And Haberl and Parapatitz showed about 10 years ago the following result. If you have such a functional measured valued valuation that is in addition continuous, non-negative, translation invariant, and SLN contravariant, then this is the case if and only if it's a linear combination of the surface area measure and the surface area measure of the reflected convex body minus k. Okay, so I think this is a well-known notion, the surface area measure of a convex body. So if you want, you take the n-1 dimensional Hausdorff measure restricted to the boundary and push it forward through the Gauss map. This gives you the surface area measure on the sphere. And this is a characterization of surface area measure by Christoph Haberl and Lukas Parapatitz. Of course, you have to define what SLN contravariant means. And what I've said just before, the Hausdorff measure is not SLN invariant and the Gauss map isn't either, but of course you can define a surface area measure also through like differentiation using the Minkowski addition and volume, so it's maybe not so surprising that it behaves nicely with respect to special linear transformation. and this is the definition they used. They say that this measured valued valuation is SLN contravariant if you look at such integrals for any one homogeneous function, then it has such a behavior. So this is a nice behavior under special linear transformations. And this is what we are aiming for, what is kind of analogon of the surface area measure for convex functions. And this is a question that has been considered before. The answer is maybe different depending on the concrete version of the question. And let me just mention as an aside, there are other results on measure valuations on convex bodies. In particular, Wolf Schneider gave a version of Hartwiger's theorem for measured valued valuations, where he used the notion of locally determined valuations. And I don't want to use this here. I want to just use valuations and transformation properties. But in this setting, there are many results on measure valued valuations. A different author, in particular, Jonas Knör, looked at this question for measured valued valuations on convex functions. Okay. So what is the thing that we want to characterize, or what is this kind of the answer? And what we really want to get is the Monge-Ampere measure. So you can define Monge-Ampere measure in any dimension, and this is just to recall what the definition is. If everything is smooth, I just integrate over the determinant of the Hessian. And if it's not smooth, then I can use subdifferentials to define the Monge-Ampere measure in general. And this here is just now Ln, or L I will also use, is the Lebesgue measure in n-dimensional space. And this is classical definitions of Monge-Ampere measure. And I think this goes back to Alexandrov, that this operator that associates with a finite valued convex function, a Monge-Ampere measure, is non-negative, this is of course trivial, and continuous. Continuous is not so trivial. And in general, here the notation that I use is, this is a space of signed Radon measures, again with a big star topology, and this is just my way of writing a measure. I use both ways to write a measure. And this Monge-Ampere measure has nice properties when it comes to geometric transformations. In particular, its translation covariant, which is just how this is defined here. Move the function and the set where the beta where you look at the measure, of course, this is connected, and it is SLN covariant, which easily follows from the definition I've given before. So the SLN behaves like that for Monge-Ampere measure. And I will call this equiaffine covariance if we have translation at SLN covariance. And the result also requires the behavior with respect to dual translations. So if I take a convex function and I add a linear function, then this doesn't change the Monge-Ampere measure, clearly, because it's a Hessian. And this is what I want to call dual translation invariance. And Monge-Ampere measures have the valuation property. So a posteriori, it's not so difficult to see, but I think this was first pointed out by Aleska using a result of complex Monge-Ampere measures by Vloki. And we also gave a proof on this in a kind of more measure theoretic approach. And if you take this together, you get one direction of the following theorem, and the other direction is joint work with Jin Lee. So if you have a measure-valued function on convex functions, it's a continuous dually translation invariant and equiaffine covariant valuation, precisely if it's a linear combination of Lebesgue measure, so this is just n-dimensional Lebesgue measure, and a multiple of Monge-Ampere measure. And this does look a little bit like what I was aiming for, the result by Haberl and Parapatitz, but not quite, but this has some, well, the assumptions are a bit different. You could also look at this result in the dual setting, which doesn't change much. You just have to translate everything. So if you now look at functions on super coercive convex functions, and you have to put a dual in front of every word, the dual translation invariant becomes translation invariant, equiaffine covariant becomes dually equiaffine covariant, and you can imagine what it means. Then you have the same thing for the dual of this Monge-Ampere measure. This is defined as before. And this, of course, has the following nice interpretation. This is just the push forward through the gradient map of the Lebesgue measure restricted to the domain of U. Of course, something that's well known. And let me just mention as a side that you can also look at different measures to characterize them. And just as a side, Jin Lee was also looking at the characterization of moment measures, and he has some results in this direction. And I don't want to state them explicitly, they're more complicated. But I wanted to recall the definition of moment measures because they look very similar to what we had just before. This is the push forward, again, through the gradient map of this measure, defined as e to the minus ux dx. I think this was first introduced by Ilaria Fragala and Andrea Colisanti, and they called it surface area measure. And Cordero and Kartak looked at this and the corresponding Minkowski problems, and they called it moment measures, and the reason comes from Taylor geometry or something for the name. But let me stick with this conjugate Monge-Ampere measures. And this is what we wanted, so it has a certain similarity to the result by Haberl and Parapatitz. The Lebesgue measure here disappears, and since we have a little bit different assumption, we get a little bit different result. But in a certain way, I think you can argue that from this point of view, the Monge-Ampere measure and this conjugate Monge-Ampere measure both can be considered as analogues of the surface area measure. And if you don't want such strong assumption, in particular if you don't want SLN covariance or contravariance, you still can get results. So this is another result in this direction, again with Jin. If you look at continuous, now I'm looking again at finite valued convex functions, continuous, dually translation invariant, translation covariant relation that is dually simple, which means that its dual is simple, which again means that it vanishes on functions with lower dimension domain. So this means in the primal setting, in the setting of finite valued convex functions, if you have functions that are kind of don't depend on one direction, they are supposed to vanish. Then the result is that there exists completely supported Radon measure, such that this function is a convolution of this function rho and this Monge-Ampere measure, and this holds for all functions of the space. So you now get a much bigger space of solutions to this question, parameterized to this Radon measure on Rn, completely supported Radon measure on Rn. And to get to the Hartwiger case, we only have a partial result here. I'm looking at measured valued valuation, but now I want to assume that my measures are smooth. Smooth Radon measures, so I have a smooth density. Under this assumption, we have, if I have a continuous dually translation invariant rigid motion covariant valuation, then there exists and here one word is missing, the rho I are rotation invariant. There exists rotation invariant Radon measures compactly supported, again smooth, such that my function is a linear combination of these convolution of these rotation invariant measures with my Hessian measures, and this again holds for all function on the space. So in this sense, I get a characterization of Hessian measures, or their convolutions with rotation invariant measures. And this version now really looks quite a bit like what Hartwig has. So we have for each degree of homogeneity something appearing, and in this sense, this would be a kind of a measured valued version of Hartwig theorem in the functional setting. Okay, this is all I wanted to say. Thank you.